Okay, let's do the last little bit for the week here. Okay, so we just talked about the Dirac delta function. Actually, scooch back here. Now we want to actually use it to solve the problem that we had with Gauss's law and taking the divergence at a point charge, for example. Okay, so the learning objective is to learn how the Dirac delta can be used to define the divergence of a point charge. Okay, let's remember where we left off. Okay, so we've got the divergence theorem or Green's theorem or Gauss's theorem, and that basically tells us that when we integrate divergence over a volume, it should be equal to evaluating the flux through the closed surface of that same volume. But we had this problem where it didn't seem like that was true, okay? In order for that to be true, this needs to be equal, right, to the enclosed charge, which for a point charge is Q over epsilon naught, okay? And we didn't find that. We found that it was equal to 0, which is a problem, okay? And it's important that we understand here, okay, that we know that this is physically true, okay? This is real. This is happening in the real life when I calculate the flux through a surface, for example. Okay, if I could really do that in real life with some kind of meter, it would actually be equal to the enclosed charge over epsilon naught. Okay, so this also needs to be true, okay, in real life, but it's not because we got a math problem. So what we really need to do is just a trick to make the math work because we know physically it has to be true. Okay, so let's go ahead with that in mind. We're going to say that we know that this has to be true. We know that the volume integral of the divergence has to be equal to, for a point charge, Q over epsilon naught. Okay, so let me make it clear. This is for a point charge. This isn't just for any particular situation. Okay, so I can just say, all right, fine, if that has to be true, let's just let the divergence of this field, okay, be equal to Q over epsilon naught times this Dirac delta function, okay, the three-dimensional version, okay, that depends on R, which is the coordinates x, y, z, okay. Now, if I say that's true, when I evaluate this volume integral, I'm going to end up, when I substitute in what it is, what I just said that it has to be or it should be, okay, it is going to, in fact, be equal to Q over epsilon naught, okay. It feels like cheating. Okay, but what we've done here is we've created a math fix to make something that we know should be true, actually true. We made the math work, okay? All right, so let's give a little bit more meaning to this, okay? So let's recall that our differential form of Gauss's law says that the divergence of the electric field is related to the volume charge density over epsilon naught, okay? This particular bit is not a vector, it's a scalar field, but it could change with position, which is to say, if I've got some volume, the charge density across that volume doesn't necessarily have to be uniform. Just to say how general this can be, okay? I could say that rho over epsilon naught is equal to, okay, so this is, for a point charge. Basically what I just did says that rho over epsilon naught also has to be equal to Q over epsilon naught times this Dirac delta function. Okay, or I can rearrange this and say, all right, the volume charge density, or the amount of charge per volume for a point charge, is equal to Q times the Dirac delta function, which is to say that the amount of charge per volume goes to infinity when my volume shrinks down to 0, okay? So this is, again, for a point charge at the origin. Okay, so hopefully that makes sense. If I really have a point charge, that means it really doesn't take up any volume at all. It makes sense that the volume charge density for a point charge would actually be infinite. Okay, it would just be Q times infinity. So this should make sense because for a point charge, we've got our volume charge density is equal to 0, right? R not equal to 0, and it isn't equal to infinity at R equals 0. Even if I use a more general vector field that blows up, okay, so I did this for the volume charge integral to calculate the electric field, but really for any general function that blows up, because it depends on something like 1 over r or 1 over r squared, right? I have this problem where when I evaluate the divergence, it was 0 when our separation vector was not equal to 0, and then it was some other crazy thing that I didn't understand when it was. Okay, we can fix this in a similar way by now saying, okay, fine. Let's say that the divergence of that vector field is going to be equal to 4 pi times our 3-dimensional Dirac delta function, where we remember that this is the separation vector, so this is r minus r prime, okay, and this is the 3D version of the Dirac delta function that I put in there.